for like a off-close thing, arguing you guys. But like, is this a problem where like I could? So well, no, but like this is an H2. So this is like a stupid. So Martin, is this like a stupid H3?
We will start the session in 2 or 3 minutes. Beforehand, we are looking for a note taker. If someone wants to volunteer, please raise your hand. Anybody?
There's no pink box. Everyone's on camera all the time. There's no privacy. It was the only illusion of privacy before. Okay. All right. I think they track you. Well, so I really don't. I don't know if it's magic or is it a person involved. It's like all AI. Any distance possible. Maybe there's somebody looking at this thing and pointing it. That was kind of like, it is island. People doing everything. It's probably the most likely. What do you think on scoring, John? We had a bit of a meeting that went on until 9:30, and then I got this. I saw the issue number. Yeah, it's also wired. Substituted Martin checks it. Martin asked me, so you know what the goals are? Good question. So let's articulate them properly. So I needed that slightly so that we don't tackle on stupid things. But I think that, but also, yeah, I want to be getting all of it. That's the thing people from sure. So that might try to see them as well. So you should have to start. Yeah.
Okay, so otherwise people can see.
But like, am I like this an effective ping box? That's why I feel special. Oh. I'm really hoping not to make it funny. Yeah. Oh, cool. Oh, there are stickers.
Yeah, there are still.
Good.
When do we get our HTTP3 stickers?
That's,
There is a suggestion to rename the HTTP over quick mapping.
that would be good.
To HTTP3, which means at least more fun than HTTP.
Shall we start?
Yeah. Okay, shall we start?
I don't think you will turn on the mic. Not working. Use this.
Okay, shall we start? People in behind, please close the door.
Richard, close the door.
Okay, let's start. Welcome. This is second slot for TCPM meeting. And please make sure you are in the right room. And this is user not well. And please keep this in mind. If you have some concerns, you can find the same contents on the IETF webpage. And thanks for volunteering note-taking. David, thank you so much. And Media, thank you so much for taking care of Jabber. And before we start the meeting, please remind, when you speak up, please say your name at the microphone so that note-taker can track your name. And this is the agenda for today. And as we have already announced, we have a single agenda for today, which is loss detection and the congestion control in QUIC and TCP. And this is not the usual, discussion topic for TCPM working group, but I believe this will be a useful discussion for both Quick working group and TCPM working group. So I appreciate Ian and Jana for leading this effort. Thanks so much. Okay, now I don't want to waste any more time, so please go ahead, Jana.
Thank you, Yoshi. All right. So I guess we'll get started. Thank you all for being here. Awesome. So we're going to talk about, I'll make a small correction to what Yoshi said. We are not going to talk about TCP congestion control or loss detection very much, but we will talk about quick loss detection and congestion control. Specifically, we'll be talking about draft IETF quick recovery. If you haven't seen it, that's fine. You can take a look at it after this meeting. Hopefully, we'll bring enough interest for you to do so. I'm Jana Iyengar, and Ian Sweat is sitting right next to me, and we are the editors of this draft. And if you haven't seen us before or would like to talk to us now, come say hi. Next slide. Let's get started. So the goals of this presentation are to discuss quick loss recovery mechanisms. We aren't going to really talk about congestion control very much because there isn't much to talk about there. It's just new Reno, with apologies to Yu Chung, who likes to call it Reno. We are not going to discuss this very much, but I'll talk about it just very briefly. Our goal here is to learn about any egregious errors or blind spots that we might have as we walk through these mechanisms. If you go, no, that's broken, then come up and say that at the mic, please. That's partly why we are here, because we believe that TCPM has the right experts. We've gone back and forth on exactly where else we should be discussing this, but this seems like the best place to do it. And our goal also is to increase engagement with TCPM on the loss recovery mechanism, specifically in Quick. The Quick working group deals with a lot of things. Loss recovery is just one of them. And so it hasn't gotten a lot of airtime, and it hasn't gotten a lot of airtime with people who understand TCP loss recovery really well. So the goal is that once we get those people up to speed on what we currently have going on in Quick, that hopefully going into the future, we'll have more engagement with those folks. That's you folks. Next slide. Non-goals, just for the next hour, we will not redesign mechanisms here. We will not relitigate constants here. It is not to say that we can't discuss them or we should not rat hole on them. We love rat holes and we would love to have them, but let's have them in a different forum. We can either do it on GitHub or on the mailing list or in a later session, but not this time, not now. And we will not relitigate Quick's use of TCP standards. We've agreed to use RFC 6298 and 5681 and various other RFCs that are part of the TCP set as non-normative references for Quick. So our goal is to do design and build congestion control and loss recovery for Quick entirely inside of this document, but we use these as informative references. So bear that in mind. And all of these things, like I said, can be done. Just don't do them right now. But let me not stop you from coming up to the mic and asking clarifying questions or whatever it is that you might want to ask or say. But just bear this in mind as you come up to the mic. And a note, I will ask questions and I hope to get answers. I have long guns here. And if you give me a good answer or if you like your answer or whatever you say, I'll throw a long gun at you. So you can have it. All right. Let's go on. This is roughly what we'll be doing. I'll go over some relevant quick details that you may or may not be familiar with, discuss the recovery mechanisms, and discuss open questions. Before I move on, how many people have read the draft? Okay, this is lovely. How many people have not read the draft? Don't feel ashamed. Did I think some people raised their hand twice. Yeah, well, that's... how many people have read the draft and not understood it? So this is good. Hopefully, this will be, some of this will be a breeze. How many people understand QUIC itself, the Quick Transport Protocol? How many people here understand the Quick Transport Protocol? I know I'm using understand very fluidly, but if you think you do, that's fine. That's really good. Or bad. I don't know what to think of this. Is this the Quick? I think this is the Quick Working Group. Huh? Did I raise my hand? Yeah, well, I should probably have raised my hand. Anyways, hopefully there are enough TCPM folks here too who haven't been paying attention, but this also means that people have been paying attention, which is great. So it'll be a breeze to go through the first few slides. Next slide. Let's start with just the overview of what parts of QUIC are relevant. Next slide. First off, QUIC packet numbers. QUIC packets have packet numbers, not sequence numbers. Why are they called packet numbers and not sequence numbers? Because we didn't want to conflate the semantics of TCP sequence numbers with QUIC's packet numbers. Specifically, a QUIC packet is a container of things. Those things we call frames. The container, the QUIC packet, has a packet number. This is a 62-bit packet number that increments, generally speaking, by 1 for every packet that is sent out. There are multiple packet number spaces during connection setup, and we do talk about that in the draft, and we do want to have multiple loss recovery contexts for each packet number space and so on, but that's in the weeds. Generally speaking, packet number is what QUIC uses for everything. Remember that in TCP sequence number talks also about delivery ordering. That's what the receiver uses to order data in the packets that are received. Packet number in QUIC does not indicate delivery ordering. We use other things for that. Packet number is not it. So packet number is purely transmission ordering. That's very helpful, as you'll see soon. Next slide. QUIC acknowledgements. Remember I told you that packets are containers that carry things we call frames? One of those things, one of those frames, is a QUIC ACK frame. What's a QUIC ACK frame? It's basically a frame that contains acknowledgement information about what the receiver has seen so far, and also what it hasn't seen so far implicitly. So a QUIC ACK frames contains these fields. It carries the largest, it carries a largest acknowledged packet, meaning that in this ACK frame, there is a packet number that is the largest packet number that the receiver is acknowledging. The second set of fields is the ACK ranges. Think of this as your SAC blocks. It's roughly that. The third field is ACK delay. This is an explicit encoding of the amount of time that the receiver was sitting on the largest ACK before this ACK was sent. Let me clarify that. Not sitting on, but the time since the largest ACK packet was received to when this ACK was sent. So it's basically not only, but it also encodes any pause times that might be at the receiver. In particular, it encodes delayed ACK delays at the receiver. That's very useful. We don't have to infer that at the sender anymore. And the ACK frame also optionally contains, not optionally contains, it does contain 3 ECN counts, ECT0, ECT1, and CE for ECN stuff. Again, we will not go into ECN stuff here because, again, the ECN encoding Magnus talked about in TH3WG, and we're going to leave it there. Next slide. ACK generation is close but slightly different than TCP's. A receiver is expected to ACK every other packet. This is similar to TCP in that every other packet is ACKed again, but we have a 25 millisecond delayed ACK timer. We say that the receiver should ACK immediately if the received packet number is not the next expected, meaning that the largest received, you're expecting to receive packets in increasing order of packet number. If that's not the case, then you ACK immediately. Otherwise, you delay the acknowledgement. Similarly, if you receive a congestion experience code point from the network, then you go ahead and ACK immediately because you want to communicate that back to the sender as soon as possible. We have a caveat for processing more packets before sending an ACK. This is particularly useful when you're in user space because the receiver might not be scheduled right now, and by the time it gets scheduled, multiple packets have arrived and are queued up in the kernel buffers, and then the application goes and reads all of those packets. You don't want to have the receiver send out ACKs for every 2 packets there. It makes no sense. The receiver might as well drain the entire kernel queues and then send out 1 ACK that ACKs everything that it has received so far. So we want to allow for the receiver to ACK less frequently. That's not the only case where we want to ACK less frequently, but we'll talk about ACKing less frequently later, but that is allowed in QUIC. Next slide. And we'll jump soon into the recovery mechanisms. And those are all timelines, just timing diagrams, sorry. And to understand those timing diagrams, I'll introduce some notation here that will be useful. And I'll repeat this as I show the timing diagrams just to make sure that you're all clear on what you're looking at. A packet that is sent is shown with PNX. That means this is a packet with packet number X. And an ACK that is sent is shown with this notation, A, which implies ACK, followed by X, which is the largest ACK, followed by ACK ranges. If you note this particular notation for ACK, this is very similar to SAC notations with one difference. X here is greater than the ACK ranges. When you show TCP SACs, you usually show the cumulative ACK point followed by SAC blocks, and usually the SAC and always the SAC blocks are greater than the cumulative ACK point. In QUIC, what you will see is the largest ACK followed by ACK ranges. So the largest ACK is always going to be larger than everything else in that block, in that frame. Next slide. Is everything clear so far? Any questions? Any clarification? Okay, good. Because if you've not been paying attention so far, pay attention now. That's all I'll say. Hopefully you'll follow along. So QUIC and TCP are, QUIC is quite similar. It's actually the same, but you'll trip up on small things. They'll be like, oh, wait a second, that looks different, and it is. So that's sort of the thing that you'll see in these mechanisms, and I'll try to note them as we go. So QUIC uses mechanisms. It doesn't necessarily implement them in the sort of distinct ways, but it implements the functions of fast retransmit, early retransmit, tail loss probe, RTOs, and also implements spurious RTO detection. For congestion control, as I said earlier, QUIC implements Neurino. There's a very small caveat that it is the largest ACK that ends the recovery period. I won't dig into that right now, but it's an important caveat. Remember that in TCP, the recovery period is ended by the cumulative ACK point moving past the recover point. And that can often cause TCP to be in recovery mode for more than one round trip time when you have multiple losses in a window in particular. But with QUIC, you will always leave recovery within a round trip time, which is really the ideal property that we want even for TCP, but we can't have because sometimes you can't have nice things. But in QUIC we can, so we do. Next slide. And now we jump into recovery mechanisms. We will start with the favorite of the bunch, fast retransmit, also known as the 3-2-pack mechanism. So here's the first time you're going to see this timing diagram. So I'll let you take this in slightly slowly, but take it in because I'm not going to go slowly on the next one. What you have here on the left side is the sender marked as S and the receiver on the right side marked with R. And time goes downwards. Okay, so time is increasing down. And you can see that the sender is sending multiple. This is not to scale, by the way, for any definition of scale. So the left side is showing you packet numbers of packets that are transmitted. The right side is showing you ACKs that are sent back towards the sender. Okay, I hope that's clear and obvious. And that little explosion that you see there is not just for fun. It's actually showing you that a packet got dropped. And yes, it is an explosion. So the packets here are packet numbers 1 through 5 are sent from the sender. And they all go towards the receiver except packet number 2 is dropped. Packet 1 is received at the receiver, is not ACKed immediately because the receiver delays this ACK, receives packet number 3 and goes, I'm going to ACK this immediately, and sends an ACK back. If you notice, the ACK has the largest ACK of 3 and has an ACK range of 1. It acts 3 and 1 basically. Packet 4 is received. Again, the receiver acts 4, 3, and 1. 5 is received. The receiver acts 5, 4, 3, and 1. Okay. So 2 is not act. The sender sees that 3 missing reports, 3 times the receiver has, or 3 packets have been received, marking 2 as potentially lost. And after 3 dupacks, this is the packet threshold of 3, the sender retransmits packet number 2. So, question, pop quiz. What do you notice different about this than what you would see in a TCP fast retransmit timing diagram? 2 is never act. Excellent. Who said that? You get a long in, Stuart. I am so sorry about that. I just realized that I'm going to be creating a mess for the cleaning people here. I'm sorry? They're not durians. Yes, indeed. That's a good point. Thank you. Stuart picked it up. Thank you so much. Yes, that is exactly right. That is one thing. There's another thing in here. Another long gun at stake. Excellent. Daniel said 2 is not retransmitted. It is sent as 6. You get a long gun 2. I'm not going to keep doing this, by the way. As you can see, my sense of scale in this room is completely broken. So I'm going to stop this now. Sorry. If you want a long gun, come pick it up at the front. This is not going very well. I can't retransmit that long gun. Sorry. So yes, packet number 6. Packet 2 is actually sent as packet 6. This is a pretty big difference. It's a subtle point here, but it's a huge difference because this shows up later. So as you can see, packet numbers are monotonically increasing. Despite the fact that 6 actually carries data that is retransmitted from a packet number space, it doesn't matter. It simply looks at 6. Was there a question? Mike?
Microphone? Oh.
Say it, I'll repeat it at the mic. Christian?
It is on? Yes. Yeah, okay. The packet number 6 may or may not repeat the content of packet number 2.
Correct. That's a good point too. Yeah. So packet number 6 may in fact contain nothing from packet 2 in the extreme case.
Or it may contain something from packet 2 and something from something else, or
Yes.
whatever.
Good clarification point.
Okay.
Thank you. Yep. So this is partly why we're calling the draft detection, because you don't necessarily retransmit data. This is because some frames in QUIC that we want to detect as lost, we may not retransmit, and that's completely reasonable and fine. This is also true for data, application data, which an application can cancel in QUIC, and we want to detect them as lost, but we won't retransmit them.
Yeah, that's what I was going to add. It's possible that nothing gets sent.
Right.
You just declare it lost, and you're like, oh, that's fine.
Yeah.
Move on.
But we want to know that it's lost. So yeah, excellent points all. So that's fast retransmit for you. That's mostly the same. Next slide. This is something that you may be familiar with. This is often called the FAQ mechanism in Linux. It's forward acknowledgement. It comes from, it's called forward acknowledgement. The idea here is that you don't need to wait for 3 ACK packets to be received explicitly. As long as a packet is received that acknowledges, as long as an ACK is received that acknowledges a packet that is threshold distance away from a packet that you want to mark as lost, mark that packet as lost. Specifically in this case, the sender receives exactly 1 ACK. That 1 ACK acknowledges 5, 4, 3, and 1. What this means is that because packet number 5 is acknowledged, immediately the sender can mark packet number 2 as lost and retransmit it if it should be retransmitted. So this is called FAQ. It's a minor modification to fast retransmit, and it helps in cases where, for instance, ACK packets may be dropped on the floor. The other place it helps tremendously is when you want to reduce the number of ACKs that are being sent from the receiver. So this allows you to compress or not send as many ACKs as you would have otherwise to trigger a fast retransmit.
Hi, Stuart Cheshire from Apple. I have a quick question, and if this is a rat hole, we shouldn't take time on it. We just had a bunch of discussion about how 6 might not be a retransmission of 2, it might retransmit some of it and not others. Is there something in there that tells the receiver, consider this to be maybe not a repeat of 2, but recovery from that, so that it knows to go out of the duplicate ACK mode where it's ACKing every packet?
No.
So how does the receiver know that that gap number 2 will never be filled in and it can stop worrying about it?
Right. So it doesn't. That's the short answer. The short answer is that the receiver never knows that gaps will be filled. Gaps will never get filled because the sender is not going to retransmit them. But we have mechanisms in place for the receiver to stop reporting them. That's the more important thing here. So quick, by definition, a receiver has to basically think about gaps as the normal case, and that's how it operates, which is why you want to allow for fewer acknowledgements even when there are gaps. And the receiver will stop reporting some gaps after it knows that the sender has heard that at least once. That's really the goal here. So thank you for that question. Yeah, that's an important and a good question.
Hey, Stuart, I'm going to file an issue on that just to track, because I think the text is not quite as clear about what might be optimally done. I think you basically might send an immediate ACK for every single incoming packet at the moment.
Yes.
For an entire RTT, or at least it's a little bit too vague about what might happen. So I think it probably deserves clarification.
That's a good point. Next slide. So we've added one thing as we do. We've added an optional time threshold based retransmission mechanism in Quick. This allows for a sender to ignore packet thresholds and wait for a certain amount of time before it declares a packet lost. Of course, the sender is expected to receive at least one ACK that indicates that a packet has not been received before it marks it as lost. But that's the general idea here. This helps with avoiding. This helps with reordering. Reordering is one of the things that trips up fast retransmit quite a bit. And if your reordering is under a threshold of 3, that works out all right. But if the reordering is greater than a threshold of 3, a packet threshold of 3, then that causes problems. This is, again, I don't want to rattle on this right now specifically because this is the time threshold one is one of the open questions. I'm gonna ask about this at the end, and we can definitely talk about this at that point. Yeah, next slide. So yeah, time threshold allows reordering tolerance in packet space. And you can see that there's a computation that we do based on RTD. And the latest RTD that you see there in that computation is the latest RTD sample that is used. Next slide. Early retransmit. Again, something we are all familiar with, but with a small twist. So how many of you know early retransmit in TCP? 3 people. Okay, 5 people. Good. Early retransmit, the problem that early retransmit sets to solve is basically, what do you do? So remember fast retransmit, right? A sender retransmits a packet when it receives 3 acknowledgements that mark that packet as lost. Or the sender, with FAC, it's that the 3rd packet beyond it has been acknowledged. But what if there aren't 3 packets after this packet that is lost? What if there's exactly 1 packet that you've sent after this packet? You're never going to get the 3 packet gap or the 3 packet distance from the packet you're trying to retransmit or you want to detect as lost. As in this case, packets 1, 2, and 3 are sent, 2 is lost, and you receive 1 ACK that says 3 is acknowledged and 1 is acknowledged, but you're never going to get an ACK for 5, which is what you want to trigger a fast retransmit. So early retransmit, basically what it says is, we will, in this case, the sender knows that there's no 4 and 5, so the sender will retransmit 2 based on the single report that it received from the receiver, because that's all it's going to get from the receiver. There's a problem with just doing that. And I'm saying right now, ignore the time that I'm showing there in that slide. if the sender was to retransmit 4 immediately on receiving that first report, it makes itself vulnerable to simple packet reorderings, packet twiddles in particular. And so that's something that in practice happens a lot. And so the Linux implementation does this implementation of this timer for TCP. And so we borrowed that out of the Linux implementation. And we have a timer that says, if you received one, just give me 1 second, Bob. If you received one ACK, then just wait for a little while and then retransmit. Bob?
Hi, I've just realized the answer to my question. I thought X was the packet number, but it's a multiply, yeah.
Oh, sorry. Yes. So that's early retransmit for you. Next slide. And now we are going to go into the timer-based mechanisms, specifically TLP, RTO, crypto, the handshake timeouts, and things. But to do that, we need to understand the RTT measurement mechanisms in Quick. So very briefly, RTT is basically 60 to 98. There's nothing that's different about this than the standard TCP mechanisms, except for one difference. The RTT sample, we do something to make the RTT sample cleaner, so to speak. So specifically, remember that I talked about ACK delay, where the receiver explicitly encodes the amount of time that it's sitting on a packet before ACKing it, the delayed ACK timeout. Yeah, we know that, so we can remove it from the RTT measurement explicitly. Now, understand that we will bring this back later, because we do want to know how long we should wait, how long a sender should wait. But the RTT measurement is expected to be a network RTT measurement. And that's the semantic here. It's slightly different from the TCP RTT measurement, which is not a network RTT measurement. It is a expected response time measurement, basically, because it includes the delayed ACK timer. So as you can see here, the RTT measurement is the time when the ACK is received to the time when the packet was sent, minus the delay that the receiver reports in that ACK. The receiver also, or not the receiver, both endpoints also declare at the beginning of a connection the maximum that they will delay ACKs by. This is called max ACK delay, and you may be familiar with a similar max ACK delay proposal for TCP that's been floating around in TCPM. That's basically used in this case in a later thing, but this is, the max ACK delay is the repeater, is an endpoint, sorry, unilaterally declaring how long it will, what's the maximum amount of time that it will wait before sending an ACK back. And this informs how we do timeouts. So if you look at the timeout computation, the timeout RTO computation is the same as for TCP, as in 60 to 98, but there's an additional max ACK delay. Remember that the RTT sample itself does not include the ACK delay here, whereas in TCP it does. So the SRTT computation, the smooth RTT computation, therefore in Quick, does not include the ACK delay. And so when you're waiting for an ACK from the receiver, you want to compensate for that. You want to wait for the ACK delay because the receiver might be waiting for that period of time. So we explicitly add the max ACK delay in the RTO computation. So we bring it back. TLP, again, similar. We use 1.5 times SRTT. This is based off of the now defunct and expired TLP draft. But we, again, explicitly add the max ACK delay back in. And we have mins for both of these. Our min RTO is 200 milliseconds, informed by what we've seen in practice in Linux. And the min timeout for TLP is 10 milliseconds. That's completely arbitrary, I think. But it comes from the TLP, expired TLP draft. And I think it was arbitrary there as well. Next slide.
Just quickly,
Yes.
30 minutes has passed, so you have another 30 minutes. Just.
Thank you. Oh boy, this is not fun. I'm going to try and race through this. If you have questions, come up to the mic. But I want to have discussion and I want to leave some room for discussion later. Okay, so RTO is basically the same as TCP, but like I said, this is TLP. My bad. For people who don't know TLP, I'm not going to go into the details. It's the last packet of a train, the last packet that's outstanding. If it's lost, it's useful to have a quick timer that fires and sends something out. That's what TLP does. If you know TLP, this is exactly the same as TCP TLP. There's no difference at all. And it includes, as I pointed out, max ACK delay. There's one small difference in the overall mechanism. Next slide. The TCP TLP draft, which is again now defunct and expired, specifies using one TLP before going to an RTO. We do 2 TLPs because we found that this is actually helpful. So we do 2 TLPs before we give up on doing TLOS probes. That's all I'm going to say about this. Note that there's no back off here because a back off is not required. Next slide. RTO, after a TLP, if all your TLPs are getting dropped in the network, we fall back on an RTO timer. And the RTO timer is seeded as shown on the slide there. And this is, again, explicitly includes max ACK delay and has a minimum value of 200 milliseconds according to the draft right now. Next slide. And this brings us to spurious RTO detection. This is actually one of the cute things about the way the mechanisms work out in Quick. Remember, I told you that in Quick we don't repeat packet numbers, right? We never repeat packet numbers. Now, this is a bit of a pain in TCP because if you want to detect that, this is what leads to retransmission ambiguity. And when you receive an ACK for a packet, you don't know if the ACK was for the original packet or a retransmission and so on. In Quick, there is no such ambiguity because every packet carries that packet number exactly once. So in this case, this is the case where there was in fact an RTO. This is the same as the previous slide. The RTO fires, 6 is sent as a retransmission, let's say, and then is acknowledged. When the acknowledgement comes back, the sender looks at it and goes, does this ACK anything that was sent before 6? Does this ACK anything newly? Does it ACK 5, for example, or 4? If it does, then my RTO was spurious. If it doesn't, my RTO was legit. So Quick calls the RTO verified at the time that it receives the first ACK after the RTO. That is an important moment in time. Next slide, because of what's going to be shown on the next slide. If this happened, where 4 was sent, got delayed, didn't get dropped in the network, but got delayed, and eventually was received, and then the sender retransmits 5 and 6, and then receives an ACK that says 4 is ACKed, Quick calls that RTO spurious. So that is the same moment in time, the first ACK after the RTO. And that moment in time, Quick makes a decision about the RTO event itself. What this means is that Quick does any changes to the congestion controller and so on at the moment where it's able to either verify or call the RTO spurious. It does not collapse the congestion window when the RTO happens. This is again a difference from the way TCP does things. TCP collapses the congestion window on an RTO and then tries to reinstate it later. We don't do anything until we know for sure what happened. That's a difference. Next slide. And that's what this slide says basically, that if we detect the packet as spurious, later we do nothing. No changes to the congestion controller, basically. It's a no-op. But at the moment of verification, if we detect the ACK as the RTO as valid, then we apply congestion control actions. And there's some more discussion on this going on right now, but yeah, that's the shape of things. Next slide. Crypto timeout. This is the equivalent to the handshake timer in the SYN-ACK timers in TCP, except it's a lot more complicated and quick because it includes a crypto handshake. So, and we have different levels of encryption and various other things are possible there. So the general gist is that this is set aggressively. This is set aggressively because we want to recover from losses in this early stage as quickly as we possibly can. This is a critical part of the communication. This is the setup. We have no idea what's going on in the network, but we also want to be a bit aggressive. So before any RTT samples, right now 200 milliseconds is what is used. And after RTT samples, we use 2 times the SRTT for a crypto timeout. This is the timer that's used for all handshake packets, not just for the first one, but for all of them. And there's of course exponential backoff on consequent timeouts. And when the timer fires, we retransmit all outstanding crypto packets. This is again one of those things which we need a little more. We are continuing to discuss this too, and there's going to be some more clarity on the text here. But that's what it is right now. Next. And that's about the end of what we've got so far. I'll go over this very quickly. There are some potential improvements we are discussing. and things that are open questions, which we'd love your input or for you to be engaged in. The first one is generating fewer ACKs. TCP says, the spec says generate an ACK once every 2 packets. In practice, there are wireless drivers and middle boxes that compress ACKs, that drop ACKs when they know that subsequent ACKs are going to simply replace the information. And in effect, the network has fewer than 1 ACK for every 2 packets. So the question for us is, given that QUIC will not see this kind of compression and will never see it because the ACKs are encrypted inside of packets, what should we do as default? Should we do 2, because that's what the book says for TCP, or can we live with 4? Should we, what's the default? What's a good default for us to use? Because it would be nice to have a higher number there if we can live with it. This, of course, has implications to the congestion controller as well. So this is a bit of an open question. We right now have 2 in the draft, but this is definitely something that we can discuss.
A quick clarification question. Yes. It is included, will be included in version 1, or this is talking about version, we are talking about version 2?
I'm sorry, can you say that? You're talking about what?
This one
Yes.
one is will be included in version 1, or
Yes.
you're aiming for version 2?
Well, so this is in version 1.
Okay.
Version 1 says, or right now the draft says, ACK every other packet. The question is, should we change that?
John, I think he was asking kind of, are we open to making changes or improvements that are in the next 3 or 4 slides?
Yes.
In this time frame, version 1. And I think the short answer is yes, but sooner is better. And obviously at some point, it's just gonna, we're not gonna hold up, let's put it this way, we're not gonna hold up the quick drafts for an improvement here. If it's not ready and it's not obvious that it has working group consensus, either in the quick working group, TCPM, or both, then we'll just wait until.
Yeah, I think these are, sorry, I interrupted you. I was just going to say that the people are showing up at the mic, and maybe we should start the discussions with these slides, or should we go through the last couple of slides and then do it?
Can you finish this slide?
Okay. Slide you have? Just a couple more slides on questions.
Okay, let's go.
Should I finish the slides?
Yeah.
Finish your slide.
Okay, go to the next slide. Yes, clarification.
Yeah, on that question of what would be allowed in V1, would it be completely out of the question to start talking about sender control of receiver ACKs as opposed to just a new default?
No, it would not be out of the question.
Okay.
It would totally be something that's within reason. Okay, next slide. This is another one, and this is sure to have a lot of discussion, is to remove the min RTO entirely. It's something I would love to do. We would all love to do. The argument is that we've communicated max ACK delay explicitly, and we know various things. And the most important thing here is that the min RTO in TCP, it's written in 6298, was there to avoid spurious RTOs. Given that the cost of a spurious RTO isn't really that high in QUIC, there's a real question of, do we care? And if we don't care, then it really helps a lot, because it allows us to recover from RTO from RTO level losses quickly. That's a huge change. So it's something that we'd love to be able to do, and it is a question that we've discussed in the past. We've sort of held off on really rat-holing on this because we've had to work on many other things, but this is something we'd love to discuss and maybe even make happen. Next slide. There's a potential timeout simplification to combine TLP and RTO. If you have noticed this, you thought about this in the past, you would know that TLP and RTO looks very, very similar to each other. And again, in QUIC, we can basically make them exactly the same. So the point again is that we don't have to deal with the cost of a spurious RTO very much. So the question is, can we combine them and make this one mechanism?
Can you explain why the cost is lower?
Because the cost of a spurious, specifically a spurious retransmission, is lower. Because when you receive an acknowledgement, that's when we make a congestion control decision. And if it was spurious, when you receive an ACK, you know it was spurious and you do nothing to the congestion controller. Basically, QUIC will detect a spurious retransmit and not have any congestion control effect. We can talk about this later if you want. There was a slide earlier, I can go back to that.
I think what you're saying is that the cost of a RTO is when you make a change to the congestion control algorithm. right? When you make a congestion control change, that's the cost. And
That's
what you're
correct.
saying here is that there isn't a cost because we detect that it's spurious. Because
Yes.
we don't actually make the change to congestion control. We're not paying, like, the cost of the retransmit itself is the same, but the cost in terms of your modification of how you view your congestion control state is mitigated by the detection.
In fact, we should say the impact of the RTO is lower. It's not so much the cost. I mean, you are sending exactly as many bytes on the line and things like that. It's the impact.
Fair enough. There's a bandwidth cost and there's a throughput cost. The bandwidth cost doesn't change. The throughput cost does.
Stuart Cheshire, I was about to say something very similar. I think people are talking about cost differently.
Yeah.
There's a cost on the network in wasted capacity. There's a cost in terms of the throughput of the connection dropping. My other comment was about this. I agree with the first point. Whenever I read about TLP, it always just seemed to be a different fine-tuning of the timeout when there's only one packet in flight. And so I agree. Unifying those makes perfect sense.
Thank you. Maria?
So there is a spurious retransmission detection in TCP as well, right?
There is. But the 6290 does not assume that. Okay. FRTO is not required, right? That's the problem. Next slide. Praveen is in queue. Let's take that, yeah.
Okay. Praveen, sorry for keeping waiting.
Hello, can you hear me?
Yes.
Yes, several things. So the TLP draft is expired, but the rack draft in TCP now subsumes TLP, and that's active. So about ACKs, generation of ACKs, right? So TCP already does stretch ACKs today because of things like LRO. So I actually don't see a big problem in moving away from 2. Because looks like the congestion controller, as documented in the quick draft, already does like appropriate byte counting without any limit. So in terms of congestion control, there's not a big problem if you're hacking less frequently because you're already counting bytes hacked. So that seems fine. And in terms of combining TLP and RTO, implementation-wise, the TCP implementation, at least in Windows, already kind of uses the same timer for it. So it kind of makes logical sense. They're never active together and they follow each other. So it would make sense to combine them.
I mean, there's a small difference, right? In that it's the earliest outstanding versus the last packet sent for TLP.
Right, there's a state machine involved, but I'm saying you could end up using the same timer if that's what you were saying.
That is true. Yes, it's the same timer for sure. Yeah, that's good feedback. This is the last slide. Again, questions on fast retransmit. How do we deal with the packet-based and the time-based one? The time-based one is really not present in TCP standards. It's there in code to some degree for the early retransmit, for instance, but it's something that we are thinking about. Folks have been experimenting with it, with the time-based thresholding in Quick, and so that's something that we are interested in considering moving forward as well. And I'll end the presentation now. Open the floor for questions. We have 12 minutes.
Subodh, I was wondering, when you mentioned unifying the TLP and RTO behavior, do you mean that unifying the effect of the RTO verified as well, or eliminating RTO verified in that case?
You couldn't eliminate the RTO verified because you want to detect. So here's the way to think about it. Call it all retransmissions. We're just going to do it aggressively, that's all. And we can do it aggressively because we're going to do the verification later. So maybe one other way to think about it is eliminate TLP and just do RTO more aggressively.
So the effect of an ACK of a TLP is different from the effect of currently in the quick drafts, the effect of ACK on TLP is different from the effect of ACK of an RTO, which is an effective ACK of TLP just triggers packet threshold-based loss detection or packet time-based loss detection, versus RTO triggers min RTO verified and actually goes to min CWIND at the moment. So I'm wondering what you are thinking about in terms of unifying those two behaviors.
Yes, it does do that, but it also will do packet-based, right? I mean, if this was going to also trigger an
I would agree with that statement. Yeah, I don't have a clear answer for that question at the moment. Do you have?
No, I mean,
Okay.
I think so what you're saying is right. I'm trying to think about the implications on packet threshold based retransmission, and we can definitely discuss that more. But yeah, I agree that this would basically have the same effect then. So I think it maybe a better way to phrase this is to say remove TLP and just make the RTO aggressive, right?
I think one of the reasons we want to discuss this in this working group is because we think it's an area of potential improvement for both TCP and Quick. And I don't think either of us have if I had a clear answer, I would just put it up on a slide and say, we should do this. But I've been thinking about this for like a year and a half, and I haven't really come up with a very clear answer.
Yeah,
so.
I think we can do it, but we have to try and see.
Praveen, you have a question? No. It's okay.
Stuart
Cheshire again. I have a question for the Quick people and maybe the TCP people as well. Something that's puzzled me ever since I learned about this. I know you talk about the retransmission time, like TCPs, is the mean round trip time plus 4 times the variance. And what's odd about that is that those units don't match up, because the mean is at time and variance is time squared. And what that means is if you're measuring it in seconds or milliseconds, you get radically different answers. And I always assumed that back in the 80s, calculating a square root was an expensive operation on the computers at that time. In today's world, is there a better algorithm? Because intuitively what we want to do, if we assume there's some normal distribution, we want the retransmission timer to be set 3 or 4 standard deviations out, so that there's always a probability that we'll guess wrong, but we want that probability of a spurious retransmission to be sufficiently small.
It's too bad that Van Jacobson is not in the room, because I mean he was using variance, but it's not meant variance in statistical term. What was computed was actually the average delta between the measured average so far and the values, which statistically is proportional to the standard deviation. Okay. It's something like square root of 2 times the standard deviation on the bell curve, but it's
yeah, I can point you to the reference. Actually, this is discussed in, I think, the in Van Jacobson's 88 paper in an appendix. But there's exactly what Christian said.
Okay. Well, thank you for answering that question. So it sounds like it's mathematically sound. Maybe yes. Variance is technically the wrong term. But yes. Mathematically it's sound. Okay.
It's on variance of the distribution. But to your second point about are there better algorithms? Absolutely there are. And I think that's something for folks to try out. We aren't going to standardize it because we are standardizing Neurino here for a reason, right? It's easy to do. It's hard to figure out what better answer, and we don't want to spend time on that right now and here. But I think it's a good time to, after we've gotten the first round of Quick done, it's a great time for folks to start thinking about better algorithms for these things. Come on, I rushed through the last few slides so you could ask questions. Oh, no, Yoshi, I'm sorry. I didn't realize you were going up to ask questions. I wasn't talking to you, Yoshi. I was talking to the rest of this room.
This is the last one? Oh, sorry.
Last slide. Yeah, it's the last slide, yeah.
Okay, go ahead. Oh, okay.
Hello.
Hey, Praveen.
Hey, hi. So question on time-based loss detection. So I actually sent this question over to the mailing list as well. It seems to me that it kind of subsumes packet-based loss detection in the sense that the way it's documented currently, if you do time-based detection and FAC and TLP, then you don't really need to do ER. So my question was, having that Boolean variable in there just seems to be confusing things a little bit more. Yes. For what it's worth, we have never implemented ER in Windows TCP, and we seem to be doing fine. So question is
wait, can you repeat that? You don't do ER?
Yeah.
But what do you do?
It's basically FAC, TLP, and RAC.
To clarify, do you, when you do so you declare a packet lost if it's, say, 3 out of order, or if it's over the time reordering threshold?
Yes.
Is that correct?
Yeah.
Okay. We thought so. We just thank you for verifying. And that works?
Yeah.
That's definitely useful.
That's super helpful.
Yeah, so that was like one thing that is very confusing in the RFC right now, that Boolean variable that's like, actually it says the default for time-based loss detection is off, whereas TCP seems to be going the other direction where you're saying rack and DLP will subsume.
Yeah, sorry, go on.
No, that's it.
So you're absolutely right. I think neither Ian nor I we're not going to argue that the Boolean is clarifying. It's actually, that's why we have this question. And we'd like to combine, in fact, the question was, and I changed it, but I shouldn't have. How do you combine packet and time thresholds so we don't have that Boolean first? Because even with the Boolean off, you still have ER with the timer, which is kind of goofy. And so what we call time threshold based is kind of broken there. But I think, yes, I think this is something we'd like to do in V1, is to try and figure out how to fix this. So we are talking about this now. So thank you for that input. Michael
Wilson, are we now on a general question suggestion session, or is that about that slide specifically?
Yeah, no, we've been on that for 10 minutes.
Still the same slide? Or general thing? Okay.
What do you want me to do?
So,
What's the last slide?
What's the last slide? Okay. So not having followed Quick very closely, I'm not sure if that has maybe already been discussed, but I presume that X carry these continuously growing packet numbers as well, right? So that would make it very easy, or should make it very easy to do ACK congestion control, which not so long ago Ingemar has presented as, well, he said that, we may actually need something like that. I think the big issue with XCC and TCP is that it's pretty hard to figure out how many X really were lost or were transmitted. In Quick, it should be quite clear. So that will be a simple message to tell the other side to say, well, you want to reduce the ACK rate, to be adaptive in that.
That's a good point. That's a great point, actually. It's something that can certainly be done, but care has to be taken to not affect the congestion controller on the send side. Of course, we know that this has implications, but yeah, it'll certainly be an easier thing to do in Quick. The question is, can it still be done well? But yes, it's certainly something worth giving a shot.
In particular, on that, I wanted to comment that I think both the congestion controller and the application have various reasons why they might want to change or have an input on the acknowledgement strategy. So for things like, for unreliable transports, you want enough information to do congestion control, but you're much less sensitive to loss recovery delays. So as an example.
Subodh, I remember last time, I don't remember exactly when, the presentation was done on RAC about adaptive thresholds for ACK thresholds as well. I'm wondering if we're planning to keep up with that and integrate. I don't know whether we have the mechanisms in Quick at the moment to be able to do what RAC is doing at the moment with, I believe they were using DSACs or something. I don't remember, it was a while ago. But are we planning to do that work as well and set the Quick
So we aren't right now, and part of this goes to the spurious detection as well, I think, because we actually, while we do spurious RTO detection, we don't do spurious fast retransmit detection. And that's something that we could do. It's something that maybe it's worth opening an issue about. Yeah, we haven't discussed this, but yes.
Well, we have text on spurious retransmission detection now, but we don't have text on undoing a congestion window, reduction.
Right, but no, we don't apply the spurious retransmission detection on a fast retransmit. We do it only on the RTO. Yeah.
Okay, this is Yoshi Nishida from Fluor. So yeah, I have very general comment. And then, so at first, I think, Quick starting from based on TCP and then becoming compatible with TCP. But especially, when you talk about the second half of the one, the thinking, not in the draft one. This is, there are some proposals in TCPM, but it's not a working group items, So we are not planning to standardize these features, but still Quick want to utilize such kind of features. So it seems to be Quick is deviating from TCP's standard. And so I would like to understand what's the design principle Quick's congestion control loss recovery mechanism.
If I understand your question correctly, you're saying that, yes, we've deviated from the TCP standards.
Right.
And is your question, what do we then use as a guiding principle if it's not TCP standards?
Right. And then, so what's aiming for Quick? So because, when the Quick and TCP connection share the same bottleneck, then
Sure.
how much, Quick and TCP should be fair? That's my question.
So the first answer to that is we've tried to follow best practice in terms of TCP implementations. We've taken a lot of cues from the Linux TCP implementation, for example. So the thing that's sharing the bottleneck is a real TCP implementation, not the standard, right? So that's what we tried to bring into the Quick standard, is what is common practice right now in TCP. The second point is that I think some of these things make a ton of sense even in TCP, and they should totally be used in TCP too. And pretty much everything that we've discussed here has been proposed for TCP in some form or the other. TLP is a great example. There's no standard at all, but implementations do it. FreeBSD does it, Linux does it. These things should be standardized. These things should be done in TCPM, and they should, at that point, we won't have much differences.
Okay. And does this become standard RFC or experimental RFC?
The goal right now is standard stack.
Lars Eckert, yeah. So the Quick Charter says that we should basically ship what's TCP compatible. I forgot the exact wording, but basically we're not chartered to do anything beyond what TCP does. Now the question is, what does TCP do?
What does TCP
do? But the good news is also we are about to freeze the -17 drafts, which are the ones that are currently open for editing. And we try to then only update them based on implementation experience. Now, in some sense, the good news is that the recovery draft specifically, which all of this is about, hasn't actually seen a whole lot of implementation experience yet. So I expect it will be relatively easy to motivate changes to that.
Yeah.
Also because, congestion control and recovery is difficult, but it's not actually a huge amount of code that needs to change. And so I would think that we can probably get the implementers to agree that we want to keep making the recovery draft better while we are in this freeze phase, simply because so far nobody has really done much there.
Yeah.
So I think my expectation would be that although in Quick you will hear later that we're going to freeze everything and changes are going to be very, very hard and so on, I think this particular thing we actually do want to get it right, because nobody has an interest of shipping a congestion controller with Quick version 1 that doesn't work. Right?
Yeah, thank you for saying that. In fact, I think that's important for people who haven't been following the process and might want to engage now. There's room for engagement, but do it soon, because we're going to try and close even this not too long from now, but it's going to be less aggressive than the general drafts.
Tommy Pauly, Apple. Yeah, so I would agree with Lars that we should be willing to kind of iterate and update on this. Regarding kind of like how it relates to TCP and making sure it's compatible in scope in that regard, I think it's useful to distinguish kind of like the differences of what Quick has available as information and what it's kind of doing on the wire format from how it's using that information. So like it certainly has more accurate signaling to get this information. And so in that regard, it deviates from what TCP could ever do. But yes. I think what are the ways that we can kind of look at the net result of what happens for the actual bytes as opposed to the signaling to see this is equivalent to TCP in terms of how it will behave if TCP had perfect information, let's say.
I think there's one example of that. Mirya was pointing out that TCP has spurious RTO detection, for example, right? If you could assume a perfect world where TCP was doing that all the time, then absolutely I think we could have the general, more broader discussion of shall we remove an RTO. Unfortunately, TCP implementations don't all implement FRTO or some sort of spurious retransmission, spurious RTO detection. If you can assume that, then maybe we could have the conversation for just those implementations that actually do spurious, but yeah.
Yeah. So I guess just in these conversations, it could be useful to define the metric by which we determine how is this compatible with TCP, kind of the bounds of that question. Because I think we shouldn't limit what you can do for Quick, the first version of Quick.
I agree with that. I think that's, just to extend that point, I think that these are both evolving pieces of work. And I think they can learn from each other. To the extent that Quick can learn, TCP can learn from what we want to do in Quick, I think that's helpful and we'd want to engage there as well.
Okay. So meeting time over. So I have one last question. So since this discussion seems to be very active, and then we have lots of productive discussion. So we should continue the discussion on the mailing list, or you want to have another kind of session? Maybe this is a question for Quick Working Group Chair or some other AD or.
And I'd suggest that we could do something like this again in the next IETF, but I don't think we should wait until then to have discussion. But if we have discussion, we definitely expect to see changes between now and Prague. And at that point, I could come and do another update and do another session where we have more discussion.
Right.
Yeah. So Lars, I think there's actually sort of two asks here, right? One ask, and this is what I think this session was about, is please help us fix the recovery draft that we're going to ship initially with the initial set of Quick documents so that it is good and as close to TCP as we can make it, but ideally no worse, and ideally also not way more aggressive, right? So basically help us write something that the ISG will not discuss in terms of, is there still TCP or not, The second ask, I think, is longer term, and I think this is also what maybe Tommy was getting at, that there's a whole bunch of new information in Quick that can lead to better congestion control in the future, right? And that is a worthwhile thing for people to play with and think about. And this, I would expect initially maybe goes to ICCRG and maybe even stays in ICCRG. Yeah. But so Quick opens up this. I tell people that want to do PhDs in congestion control that now is a really good time because you're not limited by what TCP gave you. That's like has 25 years of PhDs thrown at it, but you have an entire new set of much more rich information that you can play with. And so I expect we'll get some pretty good proposals very soon. And they need a home somewhere, and they will go beyond what TCP does and therefore need to be published somehow for us to then use them. And I think ICCRG might be that place.
For some of it.
Yeah, so it's basically two things, right? One is help us get the Quick version 1 recovery stuff ready so that the ISG doesn't object to it. And two, help us figure out how we can build better congestion control for Quick in the future.
Yeah.
Okay.
Thank you, folks.
Thanks so much. Thanks so much.
And there are long guns here, for those of you who didn't get thrown at by me. Blue sheets, people come sign the blue sheets.